Welcome to the second webinar of the Life Green Adapt project. This webinar is intended to provide a detailed introduction to the three main treatment wetland technologies that form part of the project technology package of Life Green Adapt, showcasing technical developments that were shared with our project innovation board during our first innovation workshop held online in April 2025. The workshop was hosted by project partner ISLE Utilities. ISLE Utilities brings technologies to life. ISLE does this through its various flagship programs, working together alongside innovators to connect them with end users and potential investors. The innovation workshops ultimately promote the synergy between project innovators and experts in the water sector and relevant fields. The desired outcome of the first workshop was to cultivate relationships between project innovators and sectoral experts to help bolster the replication, transfer, and scaling of project technologies and also support their adaptability and market integration feasibility. The project technologies featured in this first innovation workshop included floating treatment wetlands, aerated vertical-flow treatment wetlands with geopolymers, and electroactive biofilm-based treatment wetlands. The session began with an introduction to the project by Luz Herrero Castilla of IMEN, an innovation and technology center based in Spain that serves as our project coordinator.
So thank you very much for being here today. My name is Luz Herrero. I am here today on behalf of a project coordination team in IMEN. I'm the head of environmental technologies in this research and technology center located in Porriño in the northwest part of Spain. So my colleagues from ISLE, they have explained the general aim of the project and the work area, which is based on resilience on infrastructure, including application of blue and green infrastructures and ecosystem-based approaches to climate adaptation. So we are a consortium of 7 partners. You can see it on the screen from several parts of Europe and with different roles in the project. We have universities like University of Aarhus with an expertise on nature-based solution and electroactive treatment wetlands. Also Limnos, who is here also today in floating treatment wetlands, and in IMEN we have an expertise on aerated ones. For sure, we need like a host for the demo site. It is Shilova, who is a company, which is the company which owns the landfill, and we have also the support from the Factor for the risk assessment, and also the Universitat Politécnica de Catalunya, UPC in Catalonia, which is in charge of the life cycle assessment and microbiology assays. Which is the climate problem we are facing. We have more than 500,000 landfills in Europe. 80% more or less are dedicated to urban waste, and 20% to industrial waste, which is the case of this project. And they have a lifespan, a very long lifespan of 140 years approximately. So we have to take care of the extreme weather events that we are facing, such as droughts and heat waves, which could cause adverse effects like fires on the landfills, and also heavy rains, which can increase the volume of leachates and also to lead to landslides and floods. Our demonstration site is located in the northwest part of Spain. Here you can see a view of the here you can say a view of the site. It is on the restoration period, and it has 2 ponds which store runoff and leachate, which are located down here, and which we have retrofitted for this project. But while the climate and the weather in this area, we have like rainfalls during all the year. We are located in the green part of Spain, so, and we have like Atlantic climate with a regular pattern of rainfall. but the summer episodes of high temperatures are increasing during the summer. It's something that is happening right now. So the main objective, as I mentioned before, is to increase the resilience of these infrastructures to face these climate problems. What about the concept? We have like a combination of blue and green infrastructures. Regarding green, we have the biotechnosoils, which is a mixture of different kind of waste to mimic like a natural floor that is being used to for the restoration period, and their aim is to prevent the landslides and also try to make the landfill more resilient. And regarding the blue infrastructures, we have like a train of treatments to treat the landfill leachate, which is stored in a pond, and also the stormwater or the runoff. We have I'm not going to explain very deeply the technologies because this is the aim of today's innovation workshop. So we have all these technologies interconnected. At the beginning, it was like a treatment train only in the upper part for the leachate and in the at the bottom part for the runoff and the stormwater. But during the construction, we interconnect all the technologies just in case we need it for for an extra treatment or polishing of the effluent. Very briefly, here you can have a look at how the Technosoils implementation during the project looked like. So a big area was restored with this mixture of waste that have similar properties of the soil. So these mixtures are being processed following the regional guidelines in our area for doing that. Here are some pictures of before and after. So it was before deploying the Technosoils, during the process, and after. Here are some pictures of June last year. So you can see that endemic plants from the area has been growing. So we have increased somehow the biodiversity, or at least to keep it in the area. And what about the water or wastewater or leachate and runoff that we have there? So we have to treat it somehow and to be sure that we are dealing and that we are achieving the thresholds that we have in the legislation for the area. Some more pictures here for the floating treatment wetlands here. So we finally have implemented floating treatment wetlands not only in the landfill for the landfill leachates, but also for the water runoff. And a picture from a couple of days ago of the aerated wetlands, how they look like. We have faced different problems during the construction, but the aerated treatment wetlands has been running from May 2023. Floating treatment wetlands planted with the vegetable species surviving in the leachate from May last year, and the electroactive wetlands has finished their startup period during the end of 2024. Another topic that the project is addressing is also the vulnerability risk assessment. Our partner factor is in charge of this, and it's also something to take into account because it's one important point for this kind of infrastructures and to set the resilience of them during the time, the lifespan. And final steps forward, what we are doing now, we are finishing the experimentation phase, currently ongoing. We're studying life cycle, cost and social impacts. We are also working, like in this innovation workshop, for good exploitation of the results, and for sure for in business models and partnerships. And another important part is to raise awareness and to make a lot of communication and dissemination activities to deliver the results to all the stakeholders that could be interested.
The next presentation during the workshop was delivered on floating treatment wetlands by Alenka Zalaznik of project partner Limnos. Based in Slovenia, Limnos is an environmental engineering company specialized in nature conservation and environmental protection.
So the leachate from the landfill, although produced in small amounts, we know is highly polluted. Analysis results, here you can see on the left, indicate that the high pH and ammonium levels are particularly problematic. Plus, ammonia gets even more toxic when pH increases. There is no standard solution to this problem, so usually some kind of pond is created on site to contain the leachate. And in this case, within the project, we took the opportunity to test the floating treatment islands and to transform the pond into the open water surface treatment lagoons. We can move on. The floating wetlands consist of a buoyant structure in which macrophytes are planted. We installed them to provide either treatment functions or habitat functions, but in this case, of course, we wanted to achieve treatment of the wastewaters. The treatment works on the same principle as in every treatment wetland. They mimic natural processes. So we have aquatic plants that support microbial growth on the roots, and they enable microbial efficiency of the treatment process. The removal occurs in the exposed roots, so it's in the center of the graph, and it removes nutrients and organic pollutants. So this is the most important part of the achievement. While the roots provide surface area for biofilm, the pond and its large volume and depth of the pool is also relevant because it provides efficient sedimentation. And on the next slide, there is a short comparison of two technologies. But the floating treatment wetland is a valid alternative to a pond aeration standard classical technology. Pond aeration is effective in both oxygenation and microbial activity, but is more energy and also more maintenance intensive compared to floating treatment wetlands. Pond aeration can be adjusted for pollutant concentrations, while floating treatment wetlands depend solely on natural processes. So together, in combination, maybe they can even provide optimal technology. Let's move on. Yes. The floating wetlands at Shiloga, and here on this at this moment, I really like to thank the team of Shiloga at the demonstration site, because it really put a lot of effort into tending and planting our treatment floating islands. So the floating islands at Shiloga are assembled from waste materials which were obtained from the landfill itself. So we took a lot of also ingenuity from the team to find suitable material, because it had to be resilient to leachate corrosion. They were also inexpensive to construct, which is of course also an important relevant. We covered around 50% of the available surface area with the islands. And these small islands are attached to the side of the pond. If we move on, we will see the most important part of the island, and these are the plants. So the biggest challenge was to find plants that could withstand difficult growth conditions, since no information on this issue was available. So the approach was more or less random. We collected several species, local available species of microfunds, and we tested them from the beginning. Most planted plants did not succeed in growing due to the combination of the high pH values and high ammonia concentrations. But on the next slide, you could see this is a photo from March this year. Through time and adjustment of the area covered, at least 3 species of plants are now proven to withstand the harsh conditions. And this is the grass, Debrosis solonifera, is the most predominant species, but also Juncus and Crocosmia. So this is good news. And on the next slide, we will say a few words about the buoyant structure itself, because it must provide enough buoyancy to hold plants above the water level, because only roots, of course, hang in the water. And the structure also must enable the plants to successfully grow through it. So the holes must be sufficient and the right size. The structure must be rigid enough to enable plants to be firmly connected on the platform, because the stability is something that they need for their successful growth. The structure also must be firm enough to withstand any weather conditions on the site, like wind or waves. And for easier disposing of material after its use, it's wise to use a single material platform, so you don't have problems afterwards with disposal of those. Let's move on now. So for us, as Limnos, this particular part of the project was also very interesting in terms of development of a better platform, and we have tested a few of those, and currently we're working on this designed styrofoam platform that has been developed, produced, and also tested. So this is like a nice side product of this project. Yes, and now we will see the efficiency results. On the next three slides, we can see that we have achieved nice treatment results solely with treatment floating wetlands. Here we can see the COD efficiency, which is around 60%, which is not bad. Ammonia removal was very good, around 80% measured. It's very encouraging, and this proves that the system can achieve adequate efficiency. On the next slide, you will see the results for nitrate removal, which is another great result, proving the existence of the denitrification process. On the right side, you have the results for phosphate removal, also very significant. This is a great benefit of more intensive sedimentation in the whole solution. And then on the next slide, we can see conductivity also reduces significantly because ions absorb on organic plant matter and sediment, and sulfate, the average removal efficiency of 46%. So on the next slide, you can see the summary of the performance and results. But still, we would like to stress that now we have the maximum coverage of the whole area. We have the right combination of successfully growing plants. It's early in the season, so we expect that even better performance will be measured this year. Let's move on. So apart from the plants and the buoyancy, there is also, as mentioned, the pond itself, which benefits the system because it provides a large volume. It enables dilution of inflow. It has an adequate retention time of the whole water quantity, and provide enough space for sedimentation process, which is also an important part of the efficiency. So the system is simple, it's robust, and acts also as a buffer in case of increased flow, because Lucy in the early presentation mentioned the climate change pressures, and these downpours are becoming more and more often. So this buffer capacity is also very important. Let's move on. We estimate that the business potential in applying such treatment wetlands elsewhere, not just on landfill leachate ponds, but also in other potential sectors and problems, is something that we can look forward, and it could be a result of this project. So this is a map of Slovenia or our landfills. Not all of them have pre-existing leachate collecting ponds, but those who do will be offered this technology in very short time. Now with this nice results, we are quite encouraged to do so. Next slide. So we can conclude that the treatment efficiency demonstrated is satisfying. It is within the range of most commonly used systems, or even slightly better, and this calls for a broader use of the technology, which we could conclude this efforts that we have managed together with the entire Life Green Adapt team. Thank you very much for your attention. The team is also here available, so for any questions you can ask. Thank you very much.
The following presentation was delivered on Aerated Vertical-Flow Treatment Wetlands with Geopolymers by Alvaro Silvaterra of project partner IMIN. IMIN is an innovation and technology center based in Spain and serves as the project coordinator of Life Green Adapt.
Thank you all for being here, and I hope you enjoy the presentation as much as I did when performing it. And now I am going to present the Geopolymer system from metakaolin and aerated vertical-flow treatment wetlands. So, another problem with this. This is the last one, okay. So, we are now in the first innovation workshop. I would like to thank to the overall partnership such a huge work they are carrying out within the framework of Life Green Adapt project. And this is Álvaro Silva. I am the project coordinator of this, and I would like to share with you which one were our thoughts when thinking about this system. So imagine that we have a extremely polluted wastewater, and we are in a remote area of Galicia. So we need a nature-based solution in order to, let's say, treat such a polluted wastewater, but with a low cost, with a low environmental impact, and with very available materials on the geography nearby Galicia. So here in the northwest part of Spain, here in Galicia, in our region, we have large deposits of natural kaolin. So because of this, let's say, these three keywords, we built up this new solution. As you can see depicted on the screen, you can see the flow chart we have installed now at Xiloga, and which it is now currently working. As Alenka said, first, we have a floating treatment wetland, and afterwards we have two different treatments working in parallel in order to compare, to get the comparison among them, and also to check if those are able to polish the firstly treated wastewater coming from the flotation treatment wetland. So, which ones were the advantages and the barriers we, let's say, think when designing this treatment? So first, the advantages. We have, as I said, we have a lot of this material in our region, so will be nice. Also, this material can be easily changeable when the metakaolin will get the threshold of being sold out. Also, this material, this treatment, enable to allow personnel needed skill to operate the system. But as disadvantages, we found that we need to develop a new productive process, because we need to transform the kaolin as the nature gives to us to metakaolin in order to have the optimal properties, in order to, let's say, reduce the amount of pollutants. Also, we have a limited absorption capacity of the material because of the physical chemical process that it is having onto the surface of the particles. And also, if lots of solids comes from the previous treatment, we have the hazards of the possibility of clogging the system, of blocking the pores of the material, and let's say having a degraded efficiency. So, which ones are the main physical chemical processes we have to prosecute in order to have this proper material? So we need the metakaolin, which will be a material able to attach organic carbon, nitrogen, phosphorus, others like cations, anions, metals, but we need to optimize the porosity, and we also need to enable the electric activation onto the material surface in order to have the attachment properly carried out onto the walls of the system. So, as you can see depicted on the screen, we have in our nature here in Galicia a material on the left, but we needed to transform it to other material on the right. So actually, in the right picture, you can see not only kaolin transformed, but also we needed to add some minerals from silicate. So, which one was the process we have to carry out in our lab in order to have the productive process to convert kaolin onto metakaolin? So the thing was, first, we have to add a vast chemical process in order to, a chemical alkaline process in order to have the, let's say, the physical and the chemical properties needed to attach the contaminants onto the surface of the material. Also, we have to more or less adapt the chemical reactives we need for carrying out the new process. Also, we need to compensate, we need to adjust the proportions of kaolin and silicate in order to obtain the new material. And also, once the material is converted onto metakaolin, we need to wash a lot the new material in order to have the new properties onto our system. But those were not only the variables we have to perform to try during the work lab. We also have to figure out the curation time, the temperature, and at the end of the process, we have to more or less know the sizing of the pieces we are going to put onto our prototype. So, as you can see, it required a lot of hours of vast work in the lab in order to, let's say, finding the new information in order to have the new material prepared for being installed in our prototype. So, after this new knowledge has been obtained, we were able to produce the material in a vast amount in order to have the enough amount of material for putting it onto our prototypes. So, as you can see depicted on the screen, we were working a lot for building up our prototypes. We have the first coarse gravel, we also have the aeration circuits, and also we have the geopolymers, and every one of them were installed out of our system, like in some bags, in order to, let's say, making easy the operation of changing the geopolymer when the threshold of sold out of the capacity of the material is achieved. So, which ones were more or less the needs we have for getting more information in our prototype? So first, we need to have a flotation treatment wetland working properly. Otherwise, we are going to have a lot of pollutants coming to our system. Also, we need to try if the aeration is needed or is not needed. If not, it's better because we are going to save a lot of aeration, meaning that we are going to save a lot of money and environmental impact. Also, we would like to know if the bag containing, let's say, the geopolymer can be outside of our reactor or have to be the box inside of our reactor. So those will be key research works when operating our system. So, which one are the technical steps? The prototype is already ongoing, but the results, I am going to present them in the second innovation workshop. So, in this point, we have to finish the experimentation. This is currently ongoing, and we think that in the upcoming months, at the end of the year, we will be able to have much more results. Also, we will be able to figure out if the polishing step, I mean either the geopolymer or the electroactive, is needed or not, because maybe the flotation treatment wetland is able to pollute a lot of contaminant load enough to fulfill the necessities we have for reaching the thresholds we have met by the authorities. Also, we are going to analyze, to evaluate the results if we need or not the aeration, as I said previously, in order to save money or not. We will see if the system provides us this information. And also, we are going to find out more information about if the internal or external geopolymer configuration, which one is better for our application. But also, we are not only in a project in which we are just trying the technical stuff. We are also facing other studies, other disciplines, in order to figure out the life cycle analysis, I mean the environmental impacts, also the costs, just to check which flowchart is better regarding not the technical stuff, but the money also. And the social impact that Life Green Adapt has in the geographic area in which we are mainly working on the project. But which one are the also other next steps of Life Green Adapt? We are going to obtain a business model. So we trust in our technology. We think that it is going to be a very good technology for being implemented not only at Xiloga, but also in many other places. So we need to know which one can be the business model for getting money from exploiting our solution. Also, we need to identify other points within Europe or around the world in which we have a similar situation in order to replicate or adaptate our solution. And also, we need to look for new partnership, new potential partners for entering new markets, new geographies, new areas in which we don't have a lot of information yet. So more or less, this is the main phase of the part of the geopolymers. As you can see, everything is related here. We need the flotation treatment wetland, we need the polishing step, and we need also the multi-approach assessment in order to fully validate our technology. So thank you very much for your attention. I am fully open to your questions. I really encourage you to ask the doubts you have, but not only now, but in the upcoming weeks or months via email. Thank you very much.
The final presentation was delivered on electroactive biofilm-based treatment wetlands by Carlos Arias of Aarhus University, based in Denmark.
We talk about intensification, and there's several forms to intensify treatment wetlands. And we have energetic, which you do aeration. Physical chemical, we use special media. Operational, you can do harvesting. We can recirculate flow, and then we have the bioelectric, which is the latest development in wetlands technology. And this is what we try to implement in Life Green Adapt. Please continue. So the idea is to have microbial electrochemistry, which is a science that is looking at how bacteria can use or release electrons. So we have this matching of microbiology, electrochemistry, and also wetland technology. Continue, please. So this is just an image of some of the bacteria that attaches to media that can release electrons. Geobacter is one of these special ones. Please continue. And this image is just showing how biofilm of this geobacter is able to create layers in material. So this is what we're taking advantage of. So we're feeding the bacteria with the BOD, organic matter, and then the bacteria is releasing electrons as a waste. So what we need is a media material that can transport these electrons from somewhere in the wetland when it's looking for an electron acceptor. Please continue. So there's plenty of microbial electrochemistry technologies, and actually there's a long history of of trying to harvest electricity from wastewaters. And this is basically what we're doing. We're taking this capacity of bacteria to release electrons, to get rid of electrons, and then that means that they're more effective because they consume high amounts of organic matter, and then they have to get rid of these electrons. Continue, please. You're going to have that. There are several ways of working, and yeah, that's fine. So what regularly has been done is having these systems with electrodes and resistant to harvest electricity, but this is not what we're doing here. Here we're using direct use of these electrons, and the bacteria will just doing the work we want. Please, next one. Continue. This is all, I mean, it's in the presentation. You guys can have it, and we can go on with this later. So basically, what has been done is using this with adding a cathode and an anode and harvesting electricity, but this is not what we're doing here. Here, what we're doing is getting rid of this cathode or anode, and the electrons are flowing freely. It's exactly what we're doing is working in what is called snorkel or just short circuit. Continue. So, like I said, our development is on the right side where we have our wetland, we have our electroconducting material, we have the bacteria, we feed, in this case, wastewaters or polluted waters that have organic matter, and the bacteria keeps on eating and releasing the electrons, looking for electron acceptor. Next one. When we were developing this technology, we were testing two types of coke. We tested that it was able to conduct electricity, and then we installed some columns. Continue, please. And we had some next one. Next one. So we set up some columns to test, and we had some with no conducting material. The two materials that we tested, and then plants and no plants, and then we got some results. Next one. That we were able to remove BOD using this conducting material. We removed some COD up to 80–90%, depending on the material. And actually, the positive thing is that the planted systems have higher capacity. Next one. In terms of nitrogen, we were able to remove about 40% of ammonium and about 20% of the nitrate. And there was also a significant difference in the material we use. Next one. Phosphorus, I'm not going to talk about. Suspended solids were very effective. Continue. And then, of course, we were able to calculate some removal constants for design purposes. Next one. Then there is something, everybody talks about, yeah, I can conduct, we can remove if there is electricity flow. So we went on and designed some electrodes that were able to verify this. So this was a breakthrough. Next one. Next one. This is fine. So this is actually our method. We had some columns, we have our electrodes, we had a converter, and we had a PC to verify that we were conducting or producing electricity that was being conducted. Next one. Next one. Sampling campaigns. I mean, these are results showing that we were able to remove anywhere from 600 milligrams to 200 milligrams in the different campaigns. And this was to determine some constants for COD removal. Next one. I'm hurrying because I only have 5 minutes. Next one.
Thank you.
Yes. Continue. This is just percentage of removal efficiencies of the different materials, and this is actually the interesting one. If you look at this graph, these green lines represent the columns that were filled with gravel, and the other two, blue and red, represent the columns that were filled with electroconducting material. And was the first time that we were able, or anybody was able, to demonstrate that there was electric flow from the bottom or from the top of the system to justify there was electron flow. We fed them with upflow, downflow, and we get similar curves. The green line is the one with gravel. There is no electric flow, while the blue and the red, which was electroconducting materials, show flow. And this justifies, and this proves that there is something that is happening, and that means that we're more effective in removing pollutants. That meaning that we can reduce the size. Next one, please. That's density potential. Continue, please. Continue. I already said the conclusion. So the idea is that so we went in big size. We designed a system that was for 250 PE. Continue. And the other systems around the world, one in Carrión de los Céspedes in Spain, one in Argentina. Continue, please. And then this is the system that is currently operating in Denmark. Continue. Next one. Yes, it's hard work. Some results. And then next one. Inlets and outlets, you can see there's difference along the treatment. And then we go to our system. So the problem we had was that pet coke during COVID increased price by about 5,000%. And so we used to buy this coke, this electroconducting material, pet coke, for about 100 euros, and then all of a sudden we're getting prices of about 1,000 euros. And our initial design that was having 3 beds came down to only having a portion of the beds, and then we had a test using sand. So we're testing a system that is about 6 square meters, and blank that is about 2.5 square meters. So continue. We have a system. Yes. So we have a layer of gravel about 20 centimeters. We have about 65, 70 centimeters of electroconducting material, and then on top we have a coarse gravel part to improve the distribution. The water, initially we started with ratio of different water concentration, different polluted waters, to make sure the plants could adapt and also to have the bacteria develop. Next one. So you can see on the bottom the gravel and the collection system. Gravel was fed with it was this electroconducting material from a local factory. Fill the bed. Next one. And then it was level. Next one. The gravel part, and you can see also the 2 square meters blank that is located adjacent to the electroconductive, and is actually treating the same water and the same loading. So we can actually compare the results. Next one. Now the system is planted and is running. We started feeding polluted waters at the concentration we're aiming at, but there is no results yet. So this has been delayed because of the price of the material. So next steps. Well, we have to test different configuration, maybe empty, fill, different pulses, recirculation. We have see if we can. Well, we already tested this, and we have a planning species we have decided, and then we have to long-term results.
The presentations were followed by a discussion and a question and answer session where attendees of the workshop were able to exchange ideas with and provide feedback to project innovators. The desired outcome of the session overall was to contribute valuable feedback towards the execution of the project's second innovation workshop held online in July 2025, the content of which will be explored in the third webinar in this series, as well as the further development of project technologies before and after the conclusion of the project at the end of December 2025. Thank you for tuning in to our webinar today.